All right, let's jump right in. Data is the lifeblood of business, right? We all know that. But actually moving it from raw storage all the way to a deployed machine learning model, well, it's often a fragmented, frustrating mess. So in this explainer, we're going to bridge that great divide. We'll demystify two absolutely critical data roles, and we're going to explore a revolutionary tech framework that unites them. Today, we're looking at the professionals who process, model, and analyze raw data, and more importantly, the cutting-edge architecture that is bringing them closer together than ever before. Here's our roadmap for today. 1. The Great Data Divide. 2. Architects, the data engineer. 3. Detectives, the data scientist. 4. Bridging the data gap. 5. Enter the Duck framework. And finally, 6. From insight to action.
Section 1. The Great Data Divide. Historically, there's been a bit of a wall between the people building the data systems and the people analyzing the data.
Think about this for a second. What actually goes into the process of transforming raw data into a structured format for analysis? If you picture all that messy operational data just sitting around in scattered enterprise systems, getting it into a structured, clean format is a monumental task. It requires a staggering amount of heavy lifting before any predictive modeling can even begin. It's like this. You've got the architect building the foundation, focusing entirely on infrastructure, pipelines, and robust systems. Then you've got the detective, whose whole job is extracting insights, finding patterns, and solving problems. Think of this dynamic as transforming a chaotic, swampy data lake into a highly curated feature store. The data engineer builds this incredibly robust, scalable reservoir and organizes the flow, right? Meanwhile, the data scientist extracts the high-value droplets to formulate precise predictions, like figuring out exactly why customers are churning or forecasting next quarter's sales. Now, if you peek at their toolkits, the contrast is wild. You can really see the difference between heavy systems lifting and analytical precision. Engineers live in SQL, Hadoop, Spark, and complex ETL pipelines: extract, transform, and load. Scientists, on the other hand, are leveraging Python, R, and statistical algorithms for deep machine learning and statistical analysis. They use completely different tools, simply because they're solving completely different parts of the data puzzle. Section 2. Architects, the data engineer. Let's zoom in on the professionals responsible for converting that fragmented operational data into dependable information. These folks are the ultimate guardians of data quality. They handle data storage and organization, pipeline development, cleaning, quality assurance, data modeling, architecture, and performance monitoring. They're constantly extracting data from CRM systems, financial databases, APIs, you name it, cleaning it up, removing duplicates, and structuring it into models like star schemas or data vaults. They ensure data flows smoothly across the entire pipeline without bottlenecks or security breaches. To put the demand for that foundational work into perspective, data engineers command an average salary of $129,000 in the US. It's incredibly competitive. Why? Well, if an enterprise has a poorly built pipeline, the downstream models fail, operational costs spiral out of control, and data latency literally cripples decision-making. Building resilient, scalable big data infrastructure is just an absolutely vital investment.
Section 3. Detectives, the data scientist. Shifting gears to our detectives, their objective is taking all that curated data and converting it into evidence, predictions, and optimized actions.
They don't just start with a dataset, they start with a business question. Their day revolves around exploratory data analysis to find trends and hidden anomalies. They build predictive models, develop advanced machine learning algorithms, handle pre-processing, and run rigorous experimentation like A/B testing. They're using pure statistics and mathematics to make sure their algorithms actually hold up against real-world unseen data.
This advanced expertise is also massively valued, earning data scientists an average of $123,000 annually. The market knows that while dependable data is absolutely a prerequisite, the shift to actionable insights extracted from that data is what actually drives true business innovation and bottom-line revenue.
Section 4. Bridging the data gap. So here is the kicker.
These aren't competing disciplines at all. They operate along the exact same data value continuum. The era of the data engineer just throwing a database over the wall to the data scientist, that is officially ending. Think about the overlap here. Source extraction and data transformation are primarily engineering-driven. But as you move down to feature engineering and model deployment, those become completely shared responsibilities. And finally, machine learning is where science takes the lead, but it's heavily enabled by engineering. The absolute best teams treat this intersection as a managed handshake. Because honestly, if an engineer doesn't understand the science, they might build a pipeline with statistical bias. And if a scientist doesn't get the engineering side, they might write a brilliant model that just cannot be deployed in a live production environment.
This massive convergence has actually birthed a whole new discipline, analytics engineering. It's the critical bridge connecting raw data pipelines directly to predictive models. It's all about ensuring semantic consistency, meaning making sure a business logic concept, like the exact definition of net revenue, is mathematically identical whether an engineer is moving it through a pipeline or a scientist is modeling it for next year's forecast. Section 5. Enter the Duck framework. So, now that we know the roles, how do they actually work together in a modern tech stack? Traditional multi-cluster architectures can be pretty fragmented and clunky, so let's look at a much more elegant solution, starting with DuckDB. This is an embedded, vectorized analytical SQL and compute engine that moves processing directly to the data. This is a real game changer because it allows scientists to process massive data sets instantly without moving everything into a local Python environment. Instead of sluggishly copying, say, 500 million rows into a Pandas data frame, DuckDB runs in process. It pushes the heavy lifting down to the data itself, operating directly on files like Parquet or CSV at blazing speeds.
Next up is Duck Lake, which is an open lakehouse table and metadata format that separates storage and compute. This is your durable governance layer. It stores historical snapshots so a model can always be linked back to its exact training data. By separating the storage from the catalog, you get a totally auditable time travel record. A data scientist can guarantee reproducibility because their machine learning model is locked to an exact, immutable snapshot of the data.
And finally, MotherDuck. This is a managed cloud platform for the Duck ecosystem, enabling collaboration, sharing, and scalable execution. Are you tired of passing fragile local files back and forth? Yeah. MotherDuck solves this by providing a cloud plane, where engineers and scientists can securely share databases and analytical results seamlessly. It takes that high-speed local engine and scales it straight to the cloud, giving you centralized governance, role-based access, and shared feature datasets without the typical friction.
But the true magic here? Dual execution. The Query Planner dynamically splits work between local client resources and MotherDuck's cloud. It literally brings massive cloud compute power to local workstations without the traditional clunky infrastructure. The Query Planner is smart enough to know when to run a task on your local laptop CPU and when to dynamically route heavy, cross-table joins up to MotherDuck's cloud, and then it merges the results for you instantly. It completely removes the friction between local experimentation and cloud-scale deployment. You can work faster than ever before. Section 6. From Insight to Action.
Let's bring this whole shebang together. We need to see how this combined expertise transforms raw enterprise data into automated business value. Because predictions don't mean much if they aren't tied to a real business outcome, right? Let's trace a complete cash application pipeline. First, data engineering comes in to extract ERP open items, like messy bank files. Next, we perform exact string matching in SQL instantly using DuckDB. We then store those governed matching tables in Duck Lake to keep our history auditable and share that structured data across teams seamlessly via MotherDuck. From there, data science takes over to predict match confidence via an XGBoost model. Ultimately, this all leads to an automated SAP invoice clearing decision application. We're taking raw financial data, standardizing it, governing it, collaborating on it, and deploying machine learning to confidently predict which payment matches which invoice, automating the clearing process entirely.
This brilliantly illustrates the unified continuum in action, moving smoothly from a raw byte of data to a fully optimized business action. Step 1, dependable data through engineering. Step 2, insightful data through science. And Step 3, actionable insight through decision engineering. You just can't skip steps here. You absolutely need the engineering foundation to make it dependable, the scientific rigor to make it insightful, and the application layer to make it a final actionable business decision.
Data engineering makes data dependable. Data science makes data insightful. This quote perfectly captures the synergy of everything we've talked about in this explainer. The Duck framework doesn't replace human expertise. It amplifies it by bringing the architect and the detective into the exact same room. Look, a weakly designed pipeline will still be weak, and a biased model will still be biased. What this technology actually does is strip away those grueling infrastructure headaches so your brilliant professionals can focus on generating real value.
So, I'll leave you with this provocative thought.
How will you leverage the Duck framework to unify your data stack and accelerate your journey from raw data to automated decisions? Are your data teams still throwing models over a fragmented wall, or are they collaborating seamlessly in a unified ecosystem? Thank you for joining me for this explainer, and I really hope this gave you a powerful new perspective on the future of data architecture. Catch you next time.